Welcome to this deep dive into one of the most powerful tools in a data scientist's arsenal, the logarithmic transformation. Have you ever wondered why researchers and analysts often log their variables before running a regression or building a model? Today, we will demystify this mathematical trick and see how it transforms chaotic data into clear insights. In the world of data, not everything grows linearly. Imagine the difference between a small village and a megacity, or the wealth of a billionaire versus a student. When we have data that spans several orders of magnitude, linear scales fail us. This is where logarithms come in. A logarithm answers one simple question: to what power must we raise a base to get this number? Section 1. The intuition of scale. Most of our daily life is linear: 1 apple, 2 apples, 3. But many natural phenomena are multiplicative. Log transformation shifts our focus from absolute differences to relative, percentage-based changes. For example, the distance between 10 and 100 on a log scale is the same as the distance between 1,000 and 10,000. This is because both represent a tenfold increase. Section 2. Taming the right skew. Real-world data, like income, house prices, or populations, often follow a power law or log-normal distribution. This means most values are small, but a few outliers are massive, creating a long tail to the right. Log transforming this data pulls in the outliers and spreads out the small values, often making the distribution look more like a normal bell curve. Section 3. Linearizing relationships. Many relationships in nature and economics are exponential. If you plot the growth of a virus or compound interest, you get a steep curve that is hard to model with a straight line. By taking the log of the dependent variable, we turn that curve into a straight line, making it much easier to analyze using standard linear regression techniques. Section 4. Fixing heteroscedasticity. One of the core assumptions of linear regression is that the variance of errors is constant. However, as values grow larger, their variance often grows too, a phenomenon called fanning out. Log transformation stabilizes this variance, ensuring that our model's predictions are equally reliable for both small and large values. Section 5. Interpreting coefficients as elasticities. In economics, we love log-log models. Why? Because if both the independent and dependent variables are logged, the coefficient tells us the elasticity. For example, if we log both price and demand, the result tells us exactly what percentage change in demand occurs for every 1% change in price. Section 6. Handling zeros and negatives. There is a catch. Logarithms are only defined for positive numbers. If your dataset contains zeros or negative values, a simple log transformation will fail. In these cases, analysts often use techniques like the log+1 transformation or the inverse hyperbolic sign to handle those tricky zero values without losing data. Section 7. Real-world case study. Let's look at the relationship between GDP per capita and life expectancy. Using raw data, the graph is a messy curve where most countries are squashed in the corner. Applying a log scale to GDP reveals a stunningly clear linear correlation, proving that while money buys health, it does so with diminishing returns on a linear scale. To summarize, log transformation is about changing your perspective from how much to by what factor. It simplifies complexity, stabilizes variance, and reveals the underlying patterns in our multiplicative world. Mastering this tool is essential for any rigorous statistical analysis. References: Gujarati D. Nunn, Basic Economics; Johnny Friend, Mathematical Statistics; Woodridge J. M., Introductory Econometrics, A Modern Approach.